So, again, my name is Miss Peel. I'm a grad student at the University of Missouri. And so what that means is I'm studying science education as a doctoral degree, a PhD. And so I do research on how students like you learn science best. And so my area of expertise is computational thinking. And so we're coming in here with some of this brand new stuff and testing it out and seeing how it helps you guys learn about biology content. So that's why you'll see like the camera set up and stuff, like they're facing towards me because this is really new. And so we're videotaping it so we can show other educators that, hey, this is what computational thinking is and this is what it might look like in the biology classroom. So I appreciate you all being here and letting me come in and teach you guys some stuff. So we're just going to try some new things out. And I really do think it'll help you guys understand some biology stuff. So even though it feels like it doesn't have anything to do with biology right now, I promise we're going to get there, okay? So we played Lightbot yesterday, right? And so, yeah, thank you. When you played Lightbot, what did you do in the programs? What was the goal of each little level that you played? To light the squares, right? And so how did you accomplish that goal? Right? You put the little squares together and that gave them directions to follow. So essentially what you were doing was creating algorithms for your Lightbot to follow. So then an algorithm, and we'll just write down these definitions so we can come back to them later. You might want to write down the examples we talked about too. They could be a good reference. An algorithm then is just simply a sequence of steps to solve a problem. So just like we just said, every level you did, you had a problem to solve and you created an algorithm of the little blocks, the sequences for your robot to follow. So we use these all the time in real life when we're following sequences or giving sequences of steps to other people. So common example is if you're giving your friend directions to your house. You're giving them an algorithm to follow so that they can get to your house. Another example I like to use is a recipe. So you're following the recipe, which is the algorithm, to create that specific type of food. So when you played Lightbot, how many of you got into procedures yesterday? All right, how many of you got into loops after procedures? All right, so we'll start. Everybody get those last? Good, okay. So next is methods. So those of you that got to procedures, what did you do to make a procedure? How was it different than the levels before? You remember?
You had to tell it to go to the procedure.
So we had like an extra little box to put more little blocks in, right? Why was that useful?
Gave you more space.
More space?
Yeah, you can just put multiple ones and only use it one time in the main box.
Okay, so tell me more about what you mean by multiple ones.
Like, if you wanted it to turn and then walk forward and light up, you could use that all at the same time instead of wasting 3 blocks in the main one.
Right, so you could put 3 blocks in your little procedure and 1 up in your main. So then a procedure is a method. So this is our second term, methods. So it's a sequence of steps that's used in many processes or repeated, and it's an encapsulated sequence of steps. So it has its own function, its own goal, it does what it needs to do, but it can be used now by calling it with one line, one word, one block, like the P1 in your procedures. So after we write this down, we'll go back and play the game for those of you that didn't quite make it there. So an encapsulated sequence of steps. And using these makes our algorithms more efficient. So once you've got this one written down, you can go ahead and open Lightbot on your computers again. And then we'll go into procedures. So if you've already played some of the procedures, you can just continue with them, but I'm just going to walk through what this is and why we might use a procedure together, and then I'll let you play some too. So this is the procedure, the first level. So we're going to need more space than the main allows us, so we're going to add the proc1 slot. Okay, so the P1 command, this little block here, tells the main command when to go down and run the blocks that are in the proc1. So when it sees P1 here, it's going to run those blocks, hits P1, and then does those P1 blocks, and then it'll come right back up to the main and continue with the remaining blocks. So if we do this together, if we want to get down to our P1, we're just going to put P1 in the main, right? If we don't ever put the P1 block up there, it's never going to jump down and run what's in the procedure. So with procedures, we can kind of try and identify the steps that we might need to call more than once. So looking at this, we can kind of see a pattern, right? This side is the same as that side, is the same as that side, right? So we might try just moving forward 3, and then our light. So let's see if that works. So now when it sees P1, it's going to jump down and run these blocks. Okay, good. So the next thing is probably a turn, right? Alright, so now we've got one side done, and we're ready to do the second side, and then after that we should be ready to do the third side. So that's the sequence that would be called 3 times to complete this. So now we can just put P1 2 more times. Right, so just like we were talking about, now we've got 1, 2, 3, 4, 5 blocks here that we would have had to put in our main program 3 times. So instead of putting 15 blocks in our main, which we don't have room for, now we've put the 5 blocks here, and our main program only has 3 blocks. So we have made this main program much more efficient. We don't have to spend as much time putting these blocks together because we can do it once and call it as many times whenever we need to. Okay, so go ahead and play a couple levels of this, and then we'll come back and start some loops. So we'll take a couple more minutes to finish the level you're on. so let's go ahead and play some loops. So we'll do that by pressing this back button twice. You should be back to this page. We'll click to the right, and we're going to play through the loop. So we'll start with the first one. Alright, so looping. We're going to use the P1 command inside of the proc. So the very last block will be P1, and it's just going to repeat those steps. It's going to do them over and over and over. So we only have one spot in our main, so the P1 has to go there. And so what are the 2 steps we would repeat, we would loop to get this one done?
Forward and on.
Forward and left. And then, so we know that that will work, we'll try it. Does what we need it to do. Now we want to repeat that, so we're just going to add the P1 at the end of that procedure. So now, it's going to repeat, 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 until all the lights are lit, all the blocks are lit. Okay? So that's a loop, so it's just repeating the sequence of steps until the blocks are lit. Okay, so go ahead and play a couple of those, and then we'll come back together and talk more about it. Make sure if you haven't played any of the loops that you're in level 3, so you can get some practice with them. Alright, so finish up the one you're on, and then close your laptop so you can exit out. We'll be done with the laptops for today, and we'll come back to our notes. You can get Lightbot as an app on your phone or your iPad or whatever too, if you're like, I need more, or one level is really bothering you. I know I had trouble putting it down until I figured out the levels. The definition of method down before we played? Yeah, okay. Alright, so in the game, the procedures you made, the P1 and the proc1 down below, those were methods. So you called the method with the P1 block, and then you programmed out what the method was in the proc1 little block section down below. So in real life, I like to think of tying my shoes as a good example of a method. So when I say I'm going to tie my shoes, there's a whole sequence of steps that goes along with that, right? We all know what that is. So when I say in conversation, oh, I need to tie my shoe, that's all I need to say because we all know what that means, right? I don't have to say I'm going to grab the left lace, I'm going to grab the right lace, then I'm going to cross them, and then, I don't need to say all of that, right? I've been able to simplify what I need to say to you because we all know what that method is. So if we were going to try and make an algorithm maybe for getting ready in the morning, right? So this is our sequence of steps for what we might do in the morning to get ready. So we're going to have some steps here, and eventually we're going to get to tie shoes, right? So this algorithm here is equivalent to the main algorithm, the blocks that you put in the main in your Lightbot. Then when we get down to our tie shoes, this is like the P1 block. So the tie shoes is the title of that method. So here we're calling the method. So we'll just label it method call. Alright, so this is where we call the method. Now our algorithm, once we get to this step, like humans, we know what tie our shoes means, right? But when we're creating algorithms, we have to assume whoever's using that algorithm maybe doesn't know. So we're gonna now write out and program the method. So this is actually the method, okay? So then we write out the steps. Maybe grab the left lace, then grab the right lace, right? And so on and so forth until we've got our shoes tied, right? So it doesn't really make sense to make methods all the time. If we're only going to use it in that one algorithm, in that one context, we don't really need to make a method. It's only useful if we need to repeat it within our algorithm or if we might use it in other algorithms. So we tie our shoes in the morning, but we might need to call this throughout the day if our shoes get untied, right? So that's why we make this a method, because if we have like our, maybe, let's say, walking. This is another algorithm, right? Maybe you use this when you're changing classes or something. There's steps here, and then we're going to call tie shoes when we need to, right? And so now we've saved space in our getting ready, we've saved space in our walking, and any other algorithm where we might need to call this method of tying our shoes. So that's an example on what a method might look like in written algorithms. So next we have iteration. So this is the looping that you guys did in Lightbot on that last level. So it's repeating a sequence of steps until a condition is met. So how did we create a loop in Lightbot? What did we do to make a loop? So you put the P1 at the end of that procedure, right? So every time we would get to that last block, it would just start over. It would repeat, repeat, repeat. So when we say until a condition is met, what condition were we trying to meet? When did it stop in Lightbot? When all the boxes were lit, right? It's going to repeat P1, P1, P1 until all of the boxes are yellow, right? So that's our game example. Then, in real life, we can kind of think of each day as an iteration, each week, each month, each year, okay? So these might be a little bit different than the loops that we did in the game, because these are not really going to stop, right? These are what we call infinite loops, or at least we hope they're infinite, right? We hope that there's going to be a tomorrow each day, right? So repeating, repeating, repeating. So this is an example of an infinite loop. What's an example of a loop in your real life where you might repeat steps until something else happens? School? Okay, tell me more.
In between, like you just keep going to classes until the day's over.
Yeah, right? So you go to a class, the bell rings, you go to your next class, the bell rings, you go to your next class until the end of the day. right? So you're repeating those steps until the condition of the day is over is met, right? All right, that's a good example. So if we were maybe to build in iteration into our getting ready algorithm, we generally do the same steps every day, right? At least during the week. So we can say repeat until it's the weekend, right? So it's a little bit easier in our regular words when we're just writing stuff, which is what we're going to do in the class. You don't have to worry about putting in the right block or anything like that. You can express it in a lot of different ways. So this one we could say repeat until weekend, or we could do something else instead where we say getting ready, right? So that's just like our P1 again, getting ready until weekend. Right? So that's one way, that's another way. You could even just draw an arrow and say until weekend. Right? So now we've got 3 different ways to kind of depict that iteration in that loop. So this one physically looks like a loop. This one's just simply saying repeating until this happens, so a little bit more colloquial, more everyday language. And then this one is like the calling the P1. So you're calling this algorithm again until that condition. Okay? So now we've got our method, and then we've got iterations here too. Iteration. Right? So next we have branching. So this wasn't part of the game, but it's still an important CT principle. And so branching is choosing a path. And so we use these as if, then, else statements. So we use these all the time just when we're talking. Like, if you haven't done your homework, then you're going to do that tonight, right? You use these conditional statements in regular everyday life. So, like choosing what to wear each day. If it's cold outside, then I'm going to wear warm clothes. Else, meaning it's not cold, I can wear cooler clothes. So if we were to write this in to our algorithm, we could say if it's cold, right, then we can wear warm clothes. Else, so we physically have our branch there of 2 different paths. Else, we can wear cool clothes. Alright, so we have a condition that we're checking. If it's cold, if that's true, then we do this. False, we do this. So we're checking a condition and choosing 2 steps based on the outcome of that condition. So there we have our branching. Okay. So next we have variables. So you've probably heard of variables in math, solve for x, right? You may have heard it in science even as dependent and independent variables with your experiments. But we're going to talk about it in terms of computational thinking as a value that can change. And so we use variables to make our algorithms universal or general. So if I wanted to create an algorithm that added 5 plus 6, it's pretty easy, right? I just say 5, if I can write a 6, 5 plus 6 equals, right? And it's going to calculate 5 plus 6. So that's great. I had my problem, I've solved it with my algorithm, right? But that is now only useful if I need to add only those 2 numbers, 5 and 6, right? So if I needed to add 10 and 11, I can't do that with this algorithm. But I can now rewrite this algorithm with variables, and then I can use it for any 2 numbers. So I can say instead of 5 plus 6, I'm going to say variable 1 plus variable 2 equals. Okay? So now I can say, when I need to use it, I'll set variable 1 equal to whatever I need, and set variable 2 equal to whatever I need. So maybe in this case I do want to add 10 and 11. So now I can use it for any two numbers, to add any two numbers together that the user can set. And if I wanted to make that even more generalizable, I could make this a variable 2. Okay, so variables don't have to be numbers. They can be equal to words, they can be equal to symbols, they can be equal to sentences. We can really set them to whatever. So that value that changes doesn't have to be a number. So here if I want to make this maybe command instead of the plus sign. So now the user can then set command equal to whatever they want, right? It could be plus, it could be minus, it could be divide, and it could be multiply. So we had an algorithm that was good for only one purpose. Then we had an algorithm good for as many numbers as we needed to, but they could only be added. And now we've got an algorithm that can be a lot of different things, right? It can be any numbers. We could add, subtract, divide, or multiply any two numbers. So we went from something very, very contextualized or something really specific to something really, really general that we can use for a lot of different purposes. So if we're looking at our getting ready algorithm here, I think we've already got some variables built in. So what can you identify that might be a variable? What's a value that might change every day in what we've gotten so far? Shoes. Okay, so the type of shoes we might wear might change. Okay. How do we decide what shoes we might wear?
What we're doing.
With what you're doing? Okay,
Because
so
if you're working in a shop, you don't want to be wearing flip-flops because you could drop a hammer on your foot and it'll hurt more.
right? Okay. So again, we might check using an if statement. Well, we might check the weather, we might check if it matches what we're wearing that day, if it makes sense for what we're doing that day. So we can even tie in more branching statements to decide what the value of shoes would be that day. What else? Do we have any other algorithms in there? Clothes? Alright, so we have wear warm clothes and wear cool clothes. So if we wanted to really make these variables, we could, instead of say wear warm clothes, we could say set clothes equal to warm. Okay? So again, just a couple different ways to set that value of the variables. Okay? So we'll just put squares around our variables here. So a variable then has the square around it. Alright, so we've got variables we just did. We've got our iteration with the repeating. We've got the call method and the method actually written out over here. And then we've got our branching in our getting ready algorithms. Any questions on any of this stuff? Alright, cool. So what we're going to do is we're going to practice using some of these CT principles. So the whole point of this, to get back to like real life and biology outside of Lightbot, is to create algorithms of processes. So we're going to practice this by having you in your partners where you're sitting, creating algorithms of your process for getting ready each day. So try and use branching, iteration, methods, and variables, and when you use them, label them kind of like what we've done up here. You can label them however you think it works best. It doesn't have to be the square around the variable, but as long as I know you're using a variable. Then we're going to take this farther throughout the rest of the unit, and you're going to start making algorithms for how antibiotic resistance occurs and how maybe natural selection occurs too. So then we're going to get into applying it to the biology. Any questions? All right, we'll get started with creating your algorithms.
Grab some expos guys up here or the Spark or on board, Lisa.
Addie, can you- Yeah.